Do you know the circular fixation, which is this, can highly cause ankle stiffness? Other ankle injuries, like ankle sprain for example, may also lead to the state where the ankle joint becomes stiff. According to Bilska, the direct and non-direct cost of ankle rehabilitation is reported to be between the range of $2,000 and $5,000 per person. In addition to that, in many cases, ankle rehabilitation process can take up to few months to be fully recovered. Assalamu alaikum wa rahmatullahi ta'ala wa barakatuh. My name is Ammar Ahmed Mahdi Dokhan, and today I'll be presenting my FYP topic, which is autonomous mechanism to prevent ankle stiffness following to the circular fixation through dynamic splint. I'll be presenting these 6 outlines, and I'll try to be straight to the point, informative and interesting at the same time. Before explaining the problem statement, I made this to illustrate more and to have better understanding. So this basically represents the patient leg, and this is the foot, and this is the ankle. The motion at this direction is called dorsiflexion, while the motion at the other direction is called plantar flexion. So dorsiflexion and plantar flexion. Coming back, ankle stiffness is one of the complications for the patient with fractured leg. Due to gravity force that lead the ankle joint into plantar flexion, which cause a problem, which make the ankle become stiff. Active dorsiflexion is usually limited due to the pain at the fracture side, which has the circular fixation. Thus, patient needs an assistive mechanism to support the ankle joint motion to prevent ankle stiffness. And it is true that prevention is better than the cure. It's easier to stop something from happening, which is ankle stiffness, than repairing the damage after it has happened, which is going through rehabilitation process, which can take time and money. The main objective of the project is to develop autonomous system that can assess the dorsiflexion motion following to the circular fixation of bone post injuries. It can be subdivided into 3 sub-objectives, where the first is to design a universal mechanical design of dynamic splint mechanism, and the second to develop smart controller algorithm for autonomous systems operation, and the last one to fabricate the mechanism and test on recruited subject. The project methodology could be divided into 6 phases. The first phase is literature review, and the second phase is collection of anthropometric data from human lower extremity and particular parts that's involved in the design of the mechanism. And anthropometry is the study of the human measurement. This data is so important for the design of the mechanism. The third phase is the design of the dynamic splint mechanism, and the fourth phase will be fabrication process for this mechanism. In the fifth phase, the dedicated controller algorithm will be developed, and lastly, for the sixth phase, testing mechanism and report all the results which will be collected from the system performance. The flowchart of this system, the flowchart of this project, and Gantt chart are attached in the report.
Hi again. For the literature review, I decided to use slides since it's better to explain the figures and the tables more clearly. For the outlines for literature review, I'll be presenting the introduction, human ankle structure, classification of ankle rehabilitation robot, and related works. For the introduction, when I tried to search on Google for ankle dynamic splint, what I found is basically this. These are existing products, and they are used to immobilize the joint. The issue with these products it doesn't have any type of actuation, which is not really related to my topic. And instead, I tried to use different keyword as I inserted the keyword robot. After I inserted the keyword robot, I found so many results, as I'm going to show in the next few slides. Human ankle structure. It is important to understand the human ankle structure in order to have better mechanism design. Because human ankle has 2 separate joints, the ankle joint and the subtalar joint, where the first is called ankle joint and the second is the subtalar joint. These 2 joints allow motion in 3 different planes. Therefore, the foot can perform 3 different rotational motion. Like basically, it has 3 degrees of freedom, where the The first one is plantar flexion and dorsiflexion, and the second is adduction and abduction, and the third is inversion and eversion. As we can see here, the figure shows the 3 different planes for the 3 different motion. Like for example, for the first plane is sagittal plane, and the movement for plantar flexion and dorsiflexion. And this is maximum range of the range of motion of maximum allowable motion. Like for example, maximum allowable motion for the human ankle is up to 45.8 degree, while dorsiflexion is up to 29 degree, and the inversion is up to 22 degree, and eversion up to 17, and adduction up to 36, and abduction up to 25. But what my topic is more related to the first plane, as I'm going to design a system that has 1 degree of freedom to allow the motion in plantar flexion and dorsiflexion. As I did earlier, we are designing a system that can assist the dorsiflexion motion. So I'm more related to the first type of movement, which is plantar flexion and dorsiflexion. It actually has maximum allowable motion. It can eventually prevent the ankle stiffness. So classification of ankle rehabilitation robot. After I used the ankle robot keywords, I found so many results, but most of the articles that I read is basically categorizing the rehabilitation robot into 2 types for the ankle. One is called platform-based robot, and the second is wearable robot. For the first type, it requires the patient to place his or her foot on mobile platform. Platform-based robots are bulky, they are stationary, and they are capable of transmitting force and torques in different directions, since platform-based robots are usually designed with many actuators. And it's basically used for rehabilitation after ankle injury. While the other type, the example, one of the most popular example for this is Roger ankle robot, where it is based on steward platform, done by the author Giron, as I'm going to explain later on related works. Where the second type is called wearable robot, and sometimes it's called active orthesis as well. These robots can be worn. So as the name suggests, they are wearable, so the patient can wear it, and it's actually used to support the ankle during walking, especially for post-stroke patients, because post-stroke patients usually have weak muscles. So when they walk, sometimes they fall. So they use the wearable robot to support the ankle when practicing normal daily activity, for example, walking. And wearable robots are smaller in size and have less actuator. Just to distinguish between these 2 types, wearable robot, basically we can define it as a robot that doesn't require any type of supporting except the leg itself. Like there is no need for any external supporting except the leg. So all the system is attached to the leg, and it can be worn, as I said. And one of the most popular example for this is active ankle foot orthesis. Okay, coming to the last, which is related words. I have read like up to 15 articles, and I collected and summarized all the information for 10 articles, these 2 tables, where the first is the author name, and second robot type, degree of freedom, range of motion, and actuator type. As we can see here, the first is Anderson, and the robot type is wearable, and range of motion for it is plantar flexion and dorsiflexion. The electric motor. The second is Giron, and the year is done is the 2000, and robot type as platform based. The range of motion is actually allowed in all different planes: plantar flexion, dorsiflexion, inversion and eversion, and adduction and abduction. And the actuator type is basically pneumatic. And the last one is Baharwaj, which the robot type is wearable, and it allows 2 degrees of freedom, where plantar flexion and dorsiflexion, and the second is inversion and eversion, and the actuator type is pneumatic. And the fourth is Yun, done by the author Yon, and robot type is platform-based. The degree of freedom is 2, and the range of motion, 50 for plantar flexion and 50 for this dorsiflexion, and 55 inversion and 55 eversion. And the actuator type is pneumatic. The fifth one is done by Leo. It's also platform-based, and it allows 1 degree of freedom, the range of motion for plantar flexion and dorsiflexion, and use actuator as electric motor as actuator. For the seventh is done by the author Roy. It's wearable. It has 3 degrees of freedom. It allows all the different motion of the ankle, and use electric motor as actuator. And the eighth is done by the author Saglia, which is based robot. It has 2 degrees of freedom, where it allows flexion, dorsiflexion, and inversion and diversion, and use electric motor as actuator. And the ninth is wearable, done by the author Park, 2014, and it allows only one degree of freedom, which is for plantar flexion and dorsiflexion, and it's used pneumatic as electric motor. And the last two in 2015 and 2017 for the platform base, and the other for the wearable. They both allow 1 degree only of freedom. We can conclude from this table is that most of the systems, every one of them at least allow 1 degree of freedom for plantar flexion and dorsiflexion. These motions are the most motion that contribute to the human ankle motion. So therefore, the design for my my dynamic splint mechanism will be based on this degree of freedom, which is motion for plantar flexion and dorsiflexion. As I explained before, we will try to design mechanism that allows the motion for dorsiflexion in order to prevent ankle stiffness. This was all for the literature review.
All right, for the dynamic split mechanism, I designed this mechanism using SolidWorks, and for me, this mechanism is considered to be the result for this semester, because the designing and developing the smart control is going to be next semester. So this mechanism represents my chapter 4 for this semester, which is the result. The challenging part for me was how to design this dynamic split mechanism using only limited space, because the whole leg is occupied with the circular fixator. So I'm only having this part. So this is the foot holder where the patient will place his foot, and it's representing actually the first link, which is the moving link that will perform dorsiflexion and plantar flexion, and it's actuated from this servo motor, and the servo motor has V-belts to drive and to transmit power from the motor until the link, using 2 pulleys with the same size and the same number of teeth. And this is basically the whole part is basically the second link, which is the fixed link that will hold the motor to as a supporting, using the circulation of the foot, and also it can be adjusted based on the size of the patient foot, and it's fixed. So this link is fixed and the other link is not fixed.
For the conclusion so far, the first 3 phases of this project, which are literature review, collection of anthropometric data, and mechanism design, has been done. And I'm looking forward to continuing the remaining 3 phases next semester in FYP2, which are fabrication process, developing smart controller, and this overall system. Before ending this video, allow me to thank my supervisor, Dr. Shahrul Al-Naim, for his continuous support and guidance, especially through this difficult time with the current pandemic of COVID-19. And also, thank you for watching, thank you for your time. I will upload this video to YouTube, where you can write, comment if there is any, or also if there is any questions or further information is needed, please email me at this address. Wassalamu alaikum wa rahmatullahi ta'ala wa barakatuh.